Hi and welcome to another edition of Calculus 3. Today we are going to talk about limits and continuity for functions of several variables. Let's go ahead and start by review of this topic from Calculus 1 or pre-calculus, and we are going to start with a simplified view of this continuity as opposed to the official definition. So simplified view, a curve is continuous if you can draw it with a single stroke, and it is discontinuous if you have to take your hand off the page to draw all of it. So in this case, you see that I have a vertical asymptote. I have to draw the first branch of this thing. It's going all the way to plus infinity. Then I have to take my hand off the page and reappear from the other side and continue drawing the other branch of the curve. So this function is going to be said to have discontinuity at this point, while this one appears not to have a discontinuity. Next question is, where does the discontinuity of typical functions in calculus come from? So we emphasize typical function again because the technical definition is much more extensive than what we are doing here. Source of discontinuity typically has to do with having a fraction in your formula. Let's go ahead and look at three fractions that are source of a bit of confusion and difficulty. 0 over 1, well, there's nothing confusing about that. 0 over 1 is just 0. 0 over 0 is undefined fraction. In calculus 1 you learn about finding limits, L'Hopital rule and such in association with this type of situation. The one that we are essentially concerned about in this section is 1 divided by 0. 1 divided by 0, you could say undefined, but better than that is to say if it is plus infinity or minus infinity. We are going to take a look at several functions where they exhibit this type of a behavior. The functions we are going to look at for most part are just rational functions. Rational function is just a ratio of two polynomials. So if I have, say, y is equal to 1 over x minus 2, this is a rational function. Numerator of it is 1, denominator is x minus 2. Whenever the denominator becomes 0, we are doing division by 0. The function is discontinuous. You have vertical asymptote and so on and so forth. The issue comes up with in trigonometry as well. Perhaps we are not going to see many examples of that here, but just to remind you, we have the issues of, for example, functions like secant of theta, that's same as 1 over cosine of theta. And of course, when theta is a multiple of pi over 2, odd multiple of pi over 2, this becomes 0. So you are doing division by 0 again, and your function is going to have a vertical asymptote. So if my theta is an odd multiple of pi over 2, then we are going to have discontinuity. Same issue arises if you have a tangent of theta, which is sine over cosine. So if I have tangent of theta, that is going to be sine of theta over cosine of theta. Same denominator, same issue shows up. Then if you have, well, cosecant concentrates on sine, so 1 over sine of theta. If theta is a multiple of, any multiple of, doesn't have to be any multiple of pi, or you can think about it as even multiply pi over 2, and well, cotangent suffers from the same problem because it is the ratio of cosine of theta over sine of theta. In both of these cases, when sine is 0, we have discontinuity. For logarithm of x, logarithm of x has discontinuity at x equal to 0 because we don't see a fraction here. But if a function is having a horizontal asymptote, then its inverse is going to have a vertical asymptote, and that's the reason this logarithm has a vertical asymptote at x equal to 0. So this is a quick review of functions you see in calculus that show discontinuity in themselves. Let's go ahead and take a look at the simplest type of this, which is a rational function, ratio of two functions. They are going to show discontinuity. Let's go see how. So here I've drawn a picture of x minus 3 over x minus 2. Denominator becomes 0 at x equal to 2, and well, you're going to have a vertical asymptote there. Let me highlight the vertical asymptote for you at x equal to 2. This orange line is the vertical asymptote. So what happens here, what happens is that if I want to draw it, I draw this branch. My hand here goes all the way to plus infinity. Then I have to take my hand off the page, come here and draw the other second branch of this thing. Yeah. Of course, here we see that we go from plus infinity to minus infinity. Sometimes that doesn't go like that. So in the case where the factor here as an even exponent, you see that you could go to the same infinity on both sides. So in this branch I go to plus infinity. Essentially I have to jump to the other side, take my hand off and go to the other side and come down, and that's going to be the second branch. Now you can have several of these things in a same problem. So for example, here I have the denominator has zeros as 2 and 4, and therefore I have two vertical asymptotes. As you see, again, these two orange lines are the vertical asymptotes where the function is discontinuous. And here's a bit more complicated, where denominator, the factors have different exponents. So that x equal to 2, we go to plus infinity on both sides, and at x equal to 4, due to the fact that the exponent is odd, we flip-flop from here minus infinity, we are on minus infinity here, and jump to plus infinity over there. So we say the variety of situations that can happen with a rational function in calculus 1 or pre-calculus is pretty simple, and we can categorize all the possibilities, and there isn't essentially all that complication to it. But when we go to higher dimension, we suspect things can become a bit more complicated. Very simple reason for that: there's just more room in high dimension for something unusual to happen. So in one dimension, when I'm coming to 2, so for example, suppose you're on a real number line and say it's 0, 1, and this is 2, and you're investigating the denominator of fraction like this. Well, the trouble spot is the location x equal to 2. How do you come close to 2? Well, essentially you can come either from the right or from the left. So in calculus you talk about the right limit, left limit, and so on. Well, as you might suspect, in higher dimension, suppose I'm in 2 dimension and I want to approach the origin. Well, of course I could come from right or left, but I could come from top or bottom, or I could come at some angle like this. There are infinitely many varieties of how I could approach the origin. If I want to, actually I could spiral down to the origin. So there's much more room to maneuver in higher dimension. So let's go ahead and take a look at some basic examples. Again, we are just going to concentrate on these rational functions. So I just have a polynomial here and a polynomial there, and let's not crowd the picture with trigonometry, which is going to add another complication to our problem. Right now we're just going to take a look at so let's go to our CalcPlug 3D. Here what I have drawn is 1 over x squared plus y squared. So the numerator is 1, denominator is just x squared plus y squared. Well, where does this denominator become 0? Obviously at origin. When x and y, both of them are 0, that denominator becomes 0, and we are doing division by 0. So how does it look like? Kind of like this chimney, or whatever you want, or funnel, or whatever you want to think about it. So the rupture that is happening in this function, as we approach the origin, the value of the function shoots up to infinity, just like all the other examples we had seen before. But now let's just modify this thing slightly, see what happens. So in the denominator I put something where it becomes 0, not just one point, but actually a whole list of points. So I put x squared minus y, for example. Let's go ahead and graph this one. X squared minus y. Let me write it here so that we are all clear about what we are talking about. So first example the first example that we had in one dimension is 1 over x squared. The graph of it we saw in the previous example was like this, and then in 2 dimensions I had 1 over x squared plus y squared, 2 independent variable. In 3 dimension the graph was something like this. So we had some sort of chimney here. Now instead of those x minus 2 and such, or x squared minus 4 that I had before, I am contemplating looking at the following: 1 over x squared minus y. So what's the difference between these two cases? Here, if you set the denominator to 0, the only solution that you have is that x and y are, both of them are 0, and that's why you see this chimney having an axis at x and y equal to 0. But how about here? If I set the denominator equal to 0, I find out where the discontinuity is going to happen. So I put x squared minus y equal to 0. You simplify that, you get y is equal to x squared. Well, y equal to x squared is just our familiar parabola. Now, what's the role of this parabola in our answer? The role is that on top of this parabola, we are doing division by 0, so the function is going to rupture on, go to infinity right on top of that parabola. So let me see if I can draw what's going to happen here. So suppose this is x, this is y, and this is the z-axis. So y equal to x squared, is our familiar parabola. Let's draw it down here. So what's happening is that on top of this parabola, I'm doing division by 0, so the graph will go to either plus infinity or minus infinity, depending on which side of this parabola I happen to be. So what you see in the picture is, let's go back to this. You see, first of all, this is if you see, look at this edge here, that is close to the parabola that we are talking about. The function is split into 2 pieces. One branch, or half of it, is going to plus infinity, the other one is going to minus infinity, and as you see, the 2 pieces here. Okay, so now can it get more complicated? You bet it can get more complicated. Here is an example we had just a moment ago: x squared plus y squared. You remember that was the simple funnel. We had the least amount of problem with this, understanding what's going to happen here. Now, if on the numerator I put an expression that changes its sign, so for example, if I put say 2x minus 3y. So all I did in the numerator, I put some expression, again another polynomial, simple polynomial, and then I divide. Now see what happened. We still have a funnel, but it's a, I don't know what kind of funnel they call this thing in practice, if there's any use for it. But one side goes to plus infinity, the other side goes to minus infinity, due to the effect of sign manipulation on the numerator, the fact that I have 2x minus 3y here. So the style that we go to infinity can be different now from what we have seen in calculus 1 or pre-calculus. And is that the end of the complication? Well, no. As you might suspect, there is even more. Let me introduce you to something somewhat troubling. Let's see. X in the numerator, put x squared minus y squared. Now you see the surface is kind of like a piece of paper that has been rolled up and perhaps squeezed at some place, kind of like a fortune cookie or something like that. And we have a hard time figuring out what's happening right at this central place. That is where x and y are equal to 0. X and y equal to 0, we are looking at 0 divided by 0. Is that right? That is causing a lot of problem here, and understanding it is going to take a while. So in this case, we say the function doesn't have a clear limit at the origin, unlike the other ones that were going either plus infinity or minus infinity. In this case, we are facing bigger issues than before. So as you suspect, we need to expand our vocabulary, learn new things to be able to handle these kind of functions. We are just going to talk about some basics here and leave the rest of it to you when you take an advanced course in either advanced calculus or real analysis, when they go into much more depth than we have time for it here. So let's go back to our writing board, and one of the main tools that we have when we describe limits and such is a symbol that you have seen many times. Let me just write an example of it. So when you write limit of, let me write this thing better. So limit of, let's write an example. Say x going to 2. What do you mean by that? So we are going back again in calculus 1. What was the meaning of this? We want to extend this thing to higher dimensions and see what happens. So the meaning there was, well, you are on the real number line and say 0 and say 1 and 2 and 3. So, and x is a variable that lives on this line. It can be anywhere. And when you say x tending to 2, it means you're approaching 2 in some sense. So x could be a location here or any of these. We are hovering around 2. How do you quantify how close are you to 2? So okay, let's take x and subtract 2 from it so that I know the distance, and take an absolute value so that I'm converting into a positive number, and then signify this distance by a number such as delta. So if I say x minus 2 in absolute value less than delta, it means I am considering an interval on two sides of 2, where the size of the interval is delta, half size is delta. So from here to here, this is delta. Oh, well, I better write it. I guess that's hard to see. That's delta, and x is living inside this interval. So if I want to bring x closer to 2, I make delta smaller, and that makes pushes x to be closer to 2. To make it a very rough analogy, suppose you have a dog and there is a leash on the dog. The maximum stretch of the leash is delta, and the question is, and you have tied down the leash at the point 2, where can the dog be? So the dog can be on the right or on the left at the maximum distance of delta, but perhaps somewhere closer than that. Now we want to do something similar to this in a higher dimension, like in 2 dimensions. So now I have limit of, suppose I say x and y coming close to 2 and 3. What could I mean by that? So similar idea, just the picture is in higher dimension. So the central place we have said 1, 2, and say 3. This is the point 2, 3. So again, if you think about that example of a dog or something, you have a leash of size delta. So let's draw. So this dog can now circle all over around this pole and can be inside this circle. Well, how do you describe this circle that the dog is supposed to be inside of it? Let's go ahead and pick a point x, y on this circle, and then say this distance of x, y from 2, 3. You use the distance formula, x minus 2 squared plus y minus 3 squared. That's the square of the distance has to be less than delta squared. If the leash is size delta, then dog has to be inside this region, and that inequality is going to be valid. If you want to take square root, we have to write a little bit more, but the idea is the same. So you might see either of these things in your problems or in text. Okay. Well, preparing for advanced math, there's a lot of usage for this kind of essentially putting a microscope on things and looking and seeing what's happening at any given point. They give a name to this. Well, of course you had a name already. That's an interval, that's a circle or a disk or something, but now we have a different concept in our mind, that we are kind of living in this kind of vicinity or in this place. They call it neighborhood. In English language they call it neighborhood. So this is called a delta neighborhood. That's a lengthy word, so every now and then you see different text abbreviated one way or another. So sometimes I might abbreviate it something like that, or similar abbreviation. So delta neighborhood of 2, 3 will be the interior of this circle. So this area, this is the neighborhood that we are talking about. So we are trying to quantify when we say we are coming close to 2, 3, what do we mean by that? So remember, 2, 3 is the center of the circle. That's the number being subtracted. Delta is the maximum radius, and x and y, when we say x and y less than this quantity, will be inside. So let's specify what this for this circle. If you want to talk about the interior of this thing, you say x minus 2 squared plus y minus 3 squared is less than delta squared. That's the interior of it, because you're less. If you're right on the edge, that's where you're on the periphery of the circle. X squared minus 2 squared plus y minus 3 squared equal delta squared. You are right on the edge, or sometimes they call it the boundary. If you are outside here, well, your distance from the center is more than delta. In that case, you are in the exterior of that disk. So this thing is going to be sometimes referred to as a disk of radius delta. And sometimes they use the word ball instead of a disk. a ball makes better sense in 3 dimension, but sometimes they use the word ball for any kind of dimension. Sometimes they use the word disk for any kind of dimension. You have to be careful in the context what is meant. Okay, when we start talking about neighborhoods and how close we are to a certain point and such, we naturally come to the concept of an interval. Or when you solve inequalities, you come across the concept of interval. So in 1D again, back in calculus 1 or pre-calculus, the concept of interval was very straightforward. You are on the real number line. You start from some place and end at some place. Let's call this thing A and B. If you are excluding A and B, you put an empty circle there, and perhaps you color interior. Then you have this set of numbers which you refer to it as an open interval. So open interval excludes the endpoint. Then you have, of course, the closed interval. Closed interval, different notation for that. So we have A and B included in our set. That's referred to as closed. Of course, you can have a half and half situation. You can have one side is clipped off, but the other side is included, and then you are looking at this situation. So A is so these are all A's and B's. A is excluded, B is included. No, there's no name for this thing. It's just some interval. Well, you can imagine again in 2D we are going to have even more complicated picture. Instead of this one, just like we drew before, we can have a circle or a disk whose boundary has been excluded, and we are just looking at interior of this thing. So that one, let's just pick again an example 2, 3, and let's suppose this radius is delta. If I want to exclude these, and then I want to look at any point x, y inside of the circle, then x minus 2 squared plus y minus 3 squared has to be less than the radius. And this kind of a picture, we refer to it as an open disk. Open has a connotation that the boundary has been removed. Of course, you could have a similar picture here with boundary included here, and then in that case you'll have x minus 2 squared plus y minus 3 squared less than or equal to delta squared. Just to give some numbers here to make it look like this. Suppose this is 0.2 and this is the 1 and 3. Here I can say x minus 2 in absolute value is less than 1. Here similar setup, x, so this will be 2 in the middle, so 1 and 3, x minus 2 in absolute value less than or equal to 1. Then with that equality allows the endpoints to be included. Okay, well, you can now imagine that when it comes to this boundary, we can have all sorts of complication. What points are included, what points are excluded. So if you wish, you can have a circle that in some perimeter of it is excluded, another side of it is included, and so on. And then the description of that is not going to be as simple as just these inequalities. So, and of course we have to prepare ourselves for things other than circles. So circle is of course very nice and easy to work with, but we have things other than circles to talk about. So we talk about the region. So a region is just any collection of points, any set of points in it could be in two dimension in R2 and R3. Right now let's just concentrate on R2. So suppose we are here and some strange looking region here. That could be what we are focusing on. The region could come into pieces, so there could be some points included, some points excluded. You can see that it can become a complicated picture. Okay, for a region we want to see how can we distinguish inside of it, periphery of it, the boundary of it, the exterior of it, and such. The ideas are very intuitive. What do you mean by inside? What do you mean by boundary? What do you mean by exterior? But when it comes to mathematics, we need to have exact definition so that we can lay out a very solid foundation and build on that. So when it comes to a region, you have some intuition about what is meant by the interior of it, what is meant by the boundary of it, what is meant by the exterior of it. We just talked about that for a circle, but then if I have a arbitrary region, how do I label a point as an interior point? How do I label something as a boundary point, and so on? So here is perhaps maybe I should ask you to think about how would you define an interior point. Okay, so we are trying to move away from, okay, look at this picture, here's interior, here's our exterior and such. That's good to get started, but then how do we do these things in any high dimension in more general setting? So perhaps you want to think about it for a minute or two, and if you come up with a good definition, well, you are a good candidate to become a math major. We would like to talk about majoring mathematics to you and help you in that direction. If you are also headed toward the theoretical side of engineering and such, these kind of issues do come up there. So let's go back to did you come up with the definition of what should be an interior point? So again, going back to this picture, if I am looking at some point, let's call that point, just to fix some point, I say a certain point, say x0, y0 is inside, is in the interior of this region if a delta neighborhood of that region is entirely sitting in that region. So here is the definition. We say a point x0, y0 is an interior point of let's call this region R, so that interior point of R, if delta neighborhood of it is in R. So if you can assure yourself that a neighborhood of this thing is inside the region, then that point is called an interior region. Okay, once we have that, then the next thing that comes up is what's the interior of a region R. Well, what do you think that should be? Again, good place to stop and try to practice this mathematical language. It might come strange to you, but we do need this kind of a language to go further in mathematics, and in this case it's very easy. It's a set of all interior points of the region R. Meaning, just go ahead and collect all the points for which you can draw a tiny circle so that the entire circle is inside your region. Then those things are going to constitute the interior of a region. Okay, next topic up is, you remember in Calculus 1 you had the concept of an open interval and a closed interval. And then we had the open disk and closed disk and so on. How are we going to define an open region? What's an open region? Open region if the interior of a region is the entire region itself, then we call it an open region. Every point of it, so if every point of a region is an interior point, then we call it an open region. Again, this is the kind of language that you're going to see if you take advanced classes in mathematics. You're going to see a lot more of this thing in a course called Real Analysis. This is just the basic foundation of the alphabet of that course, the concepts that we are looking at here. We're just going to take a look at these things quickly so that you have a notion about these things when you're reading your text. We are not going to emphasize them that much, but it's necessary to know the basics. Well, what was the other concept we have? We had the interior of a region. How about the boundary of a region? How do you define a boundary point? Boundary point of a region. Let's call it region R. Okay, so if I have some strange looking picture here, how would I distinguish this type of a point from this type of a point? Well, this one we are going to call a boundary. Boundary has the property that if you consider a delta neighborhood of it, you always have some points that are inside and some points that are outside of the region. So you have two categories of points in your vicinity. Points that are inside and there are points that are outside. Such a point is called the boundary point. A boundary point may or may not belong to the region itself. It just delineates who is outside from who is inside, but the boundary itself could belong to either category. So if I have a point x0, y0, itself not necessarily in the region itself, is a boundary point if every delta neighborhood of it includes points from R as well as points outside of R. Okay, so that's how mathematically we define sitting on the fence. So you're kind of you have a leg on that one side, a leg on the other side, and so on. One more definition of this category, we have the concept of a closed region. Closed region is a region. So if it so happens that if all these boundary points belong to the region itself, we call that a closed region. A region that contains all of its boundary points. So that becomes the definition of. Okay, so these are the alphabets for advanced calculus, and the concept of a limit comes up now. So when you see in our text something like limit of f of x and y as x y approaches some point, say a b, is equal to L, we want to understand what that notation means. So let's go familiarize ourselves with the exact same concept in calculus 1. So over there, let's write an example. Limit of, say, 2n over n plus 1 when, say, n goes to, let's make it infinity here. What is that limit? Hopefully everybody in this course knows what that limit is. So just a second or two, tell me what that limit is. What do you think is the limit? So if you said 2, you're on the right track. The limit is 2. To make the problem perhaps a bit more interesting, we can add some stuff here and there and make the problem a bit more complicated. But perhaps if I have here something like sine of n, the limit is still 2, but this gives a little bit of a flavor to our problem. Our approach to 2 is not going to be just going straight to 2, but we are going to have a bit of up and down. Let's go ahead and take a look at the picture, remind ourselves what did the limit mean. I chose limit at infinity so that our picture is wide and we can look at it and it wouldn't appear like chasing ants that are going to a hole in the wall and would be hard to point it out. Limits at infinity, or the horizon is much more open, we can see things a lot better. So let's go ahead, refresh our memory about that. Let me see. Here, yeah, okay. So here I prepared this little demo in Desmos. Again, I have this, you can think about the sequence 2n plus sine n over n plus 1, or you can think about the function 2x plus sine of x over x plus 1. This one you see it in calculus 1, for sequence you see in calculus 2. It's exactly the same story. So when we say the limit of this thing is 2, so here limit L is equal to 2, what does that mean? Okay, sometimes it's described by saying the function comes closer and closer to 2. Okay, that's a kind of an intuitive notion that we have. It's sort of okay for starting calculus, but as you come higher up, you'll realize saying closer and closer is not all that clear what it means. And actually, this is a picture that you can see coming closer and closer. It doesn't make that much sense. So, first of all, what does the limit mean? The limit means the following. I will playing a certain game. The game starts with me giving you a tiny number. That tiny number is called epsilon. So I can take that epsilon, make it smaller or make it bigger and so on. Making it smaller make the problem harder to you, and making it bigger make it easier to you. So what's the notion of this epsilon? The epsilon, I determine epsilon, then I ask you, if you want to show that the limit is 2, you have to find a place in the function or a place in the sequence such that after that all the future values of sequence or a function are inside this trap or inside this strip. So the trap or the strip is made centered around the limit that we are claiming, L equal to 2. We go above and below it by the amount of epsilon I give to you, and your task is to determine when the function enters that trap and stays inside of it forever. So if I make the epsilon smaller to you like this, okay, you say we are outside. Oh, here seems like a bit of a good news perhaps. I went inside, but bad news, I came outside. Okay, from here on it looks like I go inside and stay inside. The issue is determine the location such that you enter the trap and you enter the trap for good, you never come out of it. So if I make this trap tighter and tighter, you have to look harder and harder to see where is it that you enter and then stay inside. Just to be able to see it easily, let me make this trap bigger now, like this. So in this case, we see around this location, a function has entered the strip and stays inside. If you can successfully determine when the function enters, regardless of what small of an epsilon I give you, then you're winning the game and you're establishing that the limit is that number. You notice that it was a pretty long speech to say what is the limit of a function. Saying that it comes closer and closer to 2, well, perhaps that's good for a high school level calculus class, but that doesn't really do it. It is really that lengthy definition. And when we go to higher dimension, well, the concept of instead of this strip, we are going to have a ball that is tightening around a certain point, and then you have to make sure that your function falls inside a certain region. So let's go back here and try to see what the definition is going to be in this case. So first of all, we have a function that defined on some region R, and the point AB is an interior of this region, is an interior point, so that there is actually a ball inside of it, such that the entire function is defined at that ball, but perhaps with the exception of the point AB itself. So we say let f first of all be defined on an open neighborhood of AB, except possibly at AB itself. So we don't insist that at the right at AB we have to have a definition. If for any epsilon larger than 0, there is, if you can find, there is a delta larger than 0 such that f of x and y whose distance from L is less than epsilon for all x and y, for which x minus a squared plus y minus b squared is less than delta squared. If we justify this, if for any epsilon you can find the corresponding delta, then you are justified in saying that the limit of f of x and y is equal to L. So admittedly a complicated language and also a complicated procedure. We are going to be rarely applying it to its full strength and such. But let me show to you what the issue is and why are we trying to be so precise in our language. Let's look at some surfaces that, so we are going to take a look at example of surfaces where it's not quite clear what the limit of this surface is at a certain point. Let me tell you something from perhaps your kitchen. Now probably you are not going to find this thing in your calculus book. They are not going to put this picture there, but here is, we don't mind including everything. Well, this is a kind of pasta. You notice called farfalle, I guess. It looks like a bow tie. They call it bow tie pasta or butterfly pasta or something like that. You notice that is an interesting surface. Out here Well, nothing eventful is happening. If you pick a point, you can figure out what the location of pasta or dough is. But when you come to this crease in the middle, if you move around quite a bit, a little bit, you can go from the top of this pasta piece to the bottom of it by just slight movement. This is an example of a surface whose limit at this point is not clear what it is. Meaning, if you just move around slightly, you can the function itself can change quite a bit. Let me show something like this to you in a drawing. So here's an example of a function. Let's see, I need to refresh the page, and probably it's not going to work. The GeoGebra's websites typically have a bit of a delay, and we have to wait for this to show up. Okay, it took a while, sorry for that. But here's a function, kind of remotely like that piece of pasta. It's 2xy over x squared plus y squared. The question is, what's the limit of this function as x and y approaches 0? Well, if you look at the graph of this function, you notice that it's like a paper that has been folded at a certain point. You see that fold in the center. It's like somebody pinched the piece of paper at this point. Now, suppose I ask you, what's the limit of this thing as x and y approaches 0? Out here is like on the edges of this bow tie pasta. We know exactly where something is. But when we come at this center, it becomes unclear as to where we are at. Well, let's decide to approach the origin. So here in this demo says, let's take m equal to 1, meaning the slope is 1, which means we are taking x and y to be equal to each other. Y equal to x is going to be the style of our approach. We are going to approach the origin along this line. Well, if I do like that, what would be my limit? I'm going to move this point here. So what the software does is that as you change your x and y there, it tracks the value of the function, meaning this f of x and y, or the value of z for you, and you see where you're going to be headed at. So as I approach the origin, I see I'm right on the top of that crease, and I am just approaching 2. Actually, if you just put x and y equal to each other in this expression, you just get 2. The value of this function is just 2. Now let's take a different approach. I go to here is a different approach. Let me rotate the picture so you see. Now I'm taking approach of the sloping point 5. As I come close to the origin, you see that I miss my previous spot, and I am on the different set of points. If I choose still here is like slope minus 1.5. If I approach the origin along this, the graph is at below the surface, so let me just stick to the positive, like here, m equal to 3.5. If I approach the origin, you notice I'm here right now. I'm here. You notice that I'm going to a different location. So here are 3 different approaches. One, we were at the top of the crease. we came to 2, and then we had this one, we are at a different place, and the third approach we are ending up at a different location. So in this case we say the function does not have a limit. It does not have a limit as we come close to the origin. Intuitively we say, well, we could have been anywhere on this crease from top to the bottom at this pinch point, and for that reason the function does not have a limit. Let's go ahead and do this thing on paper. Suppose we consider the function, so I consider a particular function z. The example that we saw over there is 2xy over x squared plus y squared. We want to show the limit of this thing, 2xy over x squared plus y squared, as x and y approach the origin, does not exist. One standard way to show that the limit does not exist is to approach the location that you want along different directions and notice that you are getting different answers. If a limit exists, it is unique. You know that from calculus 1. If a limit exists, it's unique. So if different approaches bring you to different location, it means the function does not have a limit. So let's specify our approaches. So one approach I can come in this direction along the 45-degree line. What's this approach? On this approach, x and y are equal to each other. So instead of y we can put x, or instead of x we can put y, either one. So 2xy over x squared plus y squared, it becomes 2x. Instead of y I put x, instead of y again I put x. So this is 2x squared over 2x squared, and that's always 1. Now let's suppose I approach the origin along this line. Well, what is the equation of this line? This one, minus 45-degree line, y equal to minus x. So instead of y I put minus x. So I get 2x times minus x over x squared plus then minus x squared. So this is minus 2x squared over 2x squared, and now I get minus 1. So along this I am approaching 1, along that I am approaching minus 1, and the fact that these two are different, these two limits are different limits, as soon as we have that we can claim that the limit does not exist. Okay, you can expect problems in this section to be a bit trickier than the ones that you had in calculus 1. Actually quite a bit trickier than that, even if all that we are dealing with are just these polynomials, rational functions and polynomials and such. We still have some work to do. Okay, let's stop here, and you try to do as many exercises from this section as you can. My best advice is to read that section and read it end to end with interest until you absorb the concept, and then the future lectures are going to be a lot more enjoyable. The language might be a little bit odd for concepts that are so familiar to us: interior, exterior, boundary. Why should we have so much mathematical detail for such an easy concept? There is no avoiding it in mathematics. We have to live with the precise language of mathematics. Okay, so I stop here, and we are going to continue with more routine calculation in the future lectures. So again, I emphasize, try to read the section, the text itself as much as you can. Until then, good luck and God bless.